Hi, and welcome to Lecture 15, in my course on Introduction to Quantum Theory and Technologies. So this will be the last lecture of the series, and we are going to sort of cap it off by doing something pretty cool. This is a topic of quantum teleportation. So we're going to put together all the things that we've learnt about quantum circuits, doing quantum gates, entanglement, and all these different ideas, and achieve something which is pretty remarkable, which is to perform quantum teleportation. So, all right, so let's get started with that. So let me first basically give you an idea of what quantum teleportation actually is. So basically, the idea here is to teleport an unknown state from Alice. So there are two people involved here, Alice and Bob. They are both in possession of some qubits, so two-level systems. And initially, the state is held by Alice. So there's some quantum state which is held by Alice. And the idea is that this state should end up at Bob's side at the end of the process. And one of the key important things here is that Alice and Bob never really need to know what the state actually is. Okay, so I'll explain why that is kind of important later on. But yeah, so this is basically the final state of what we should end up with. So initially the state was here, but now finally Bob is in possession of the state. So uh, let me just sort of clarify a bit of what quantum teleportation actually is and is not. So many times you sort of have this image of quantum teleportation, a bit like how seen in science fiction movies like Star Trek and things like that, where a person steps into some kind of teleporting machine and then they sort of disintegrate, but then they materialize somewhere on, say, a different planet. This is not actually how quantum teleportation really works. In quantum teleportation, there's always like the material kind of substance which carries the quantum information, like an atom or some photon or some superconducting circuit or whatever it is. You always have the physical qubits at either end. So it's not like this atom somehow, disintegrates here on Alice's side and it materializes here on Bob's side. It's really just the quantum state that gets kind of transported, right? So the quantum state was initially here, but then finally the quantum state is at the other end at the end, right? So you might say, well, okay, well, actually, that sounds maybe not quite like teleportation. Sounds almost a little bit more like, a fax machine or something where we put in information at one end and then the information appears at the other end. Well, another way to view it is that actually, because the quantum state is actually the most fundamental representation of the state, if you have a quantum state here, it's kind of it's not really distinguishable actually, it doesn't really matter what atom is actually on because all the atoms are actually identical. They're completely identical objects, and really the thing that defines the state of the atom is actually the quantum state. So you might say actually the quantum state is the most fundamental thing anyway, not really so much the atom. And so that is what is being teleported. And another aspect is that because we know from the no cloning theorem, it's actually impossible to make two copies of the state. So in the last lecture, we did something like, say you had a quantum state here, we actually found that it's actually impossible to make a different quantum state on a different qubit. Teleportation is actually something that sort of, uh, you know, uh, it's consistent with the no cloning theorem because, of course, we don't have two copies of the state. What happens is that you have one state here, but then it sort of gets destroyed, but simultaneously created on the other side. In this way, that part of it is very much like teleportation because, um, when the guy steps into the teleporter, you don't get two copies of the people in the spaceship. One of them disintegrates and then another one materializes. So that process of kind of one being destroyed and then the other one being created is that part of it is very much like teleportation. So like any scientific kind of phenomenon with a fancy name, it's partly misleading, but generally people are pretty uh, happy with this kind of name for uh, the process that we're going to be talking about. Right? Okay, when I say people, I mean like scientists. So sometimes some scientific things people think, oh, it's named terribly badly. This is not actually one of those. Generally, people think that this is named reasonably, consistent with what it actually really is. Okay, so let's kind of talk a little bit about uh, what makes this teleportation protocol kind of something which is pretty remarkable and why we should be interested in it. Okay, at the beginning, I said that the state is actually an unknown state, right? So that means that Alice actually does not know what state she is in possession of, right? So Alice has this state here, and she does not necessarily know what it actually is. So you might think, well, that's a little bit of a weird situation. How can you have a state not know what it is? Well, such things are actually fairly common in quantum mechanics because, as I'll explain in the next few slides, it's actually not always so easy to know what state you actually have. Classically, it's always quite easy to know what state you really have because all you have to do is look at it. You go, okay, well, what is it that I have here on my computer? Oh, it's 011 010. I can easily read what the state of the computer is. Quantum mechanics is a little bit different. Often you actually may not know what the state is, right? But in terms of showing why this is important for the teleportation protocol, um, if she actually knew what it is, then it's actually not really very exciting, or you wouldn't really need the teleportation for this reason that if Alice knew what the state was, we wouldn't need this fancy teleportation method to tell what Bob state, give the state to Bob, because all she could do, or all she would need to do, is just to phone up Bob and say, "Hey Bob, I've got this state. So hi Bob, my state is alpha I over 2 beta square root of 3 over 2. So can you just go and make it where you've got it, where you've got your qubit?" And then Bob says, "Sure, I'll just do that." Bob goes and shines some lasers on it, makes that state. Okay, and then basically, you know, not really teleportation, but the aim of making this state over at Bob's side is kind of achieved. So you don't need any fancy teleportation protocol to make the state if you know what it is, right? So um, it kind of defeats if you know what the state is, then it's not really a very necessary thing to do the teleportation. So kind of it's more interesting if Alice happens to not know what the state is. So okay, so fine. Say Alice doesn't know what the state is. Okay, then well, why couldn't she just measure the state and figure out what it is, and then tell Bob what it is, right? I mean, that's what we would do classically. Say I didn't know what's the state of my computer. So what I do is I just read the state of my computer, find what that is, and tell Bob, hey Bob, I've got state 10010, right? And then Bob will go, sure, I can make a copy of that, no problem. Quantum mechanically, uh, it's it's difficult to actually know what the state is, particularly if you've only got one copy of the state. Okay, so with only one copy of the state, basically it's impossible to know what your state is if you don't know it. Because remember, when you do a quantum mechanical measurement, there's always a random collapse. So say I've got my state alpha 0, beta 1 here. So if I didn't know what state it is, then, I don't know what basis to measure it in. So, okay, why don't I just choose the 0, 1 basis, just to be certain. And say Alice measures this state, alpha, beta, doesn't know what it is. And as we've learned in the past lectures, she would get either 0 or 1 with probabilities of, say, alpha squared, beta squared modulus. Um, and say she's only got one copy of the state. Okay, well, say, just for argument's sake, she gets the outcome 1, right? She doesn't know what the state is, but she gets the outcome 1. So actually, there's not much you can actually say from that. Uh, Probably the only sure thing you can say from that is that beta is not exactly equal to 0, right? Because if beta was exactly equal to 0, then there's basically no chance to get this outcome 1, right? If beta was 0.01, then, with probability 0.0001, she could get this outcome 1, right? So, okay, we've only got one chance. There's no statistics, there's no probabilities that she can really even say. She may have been very lucky, unlucky to get 1. We really don't know. So there's not really that much that can be said just by getting a single outcome from a single measurement, because there's no information about probabilities or anything, right? So in this case, if she was trying to teleport this state and, say these guys didn't know about the teleportation protocol, maybe the best you think they could do is to do something like this, which is for Alice to measure her unknown state. Okay, she's only got one copy of the state. Then she measures it. She gets 1, so she goes, okay, well, maybe something like 1. So she goes, not sure what that is, but Bob, why don't you go and make that? And Bob goes, okay, sure, I'll make that state. Okay, so, clearly this is a method that is not going to work very well effectively, because, it is missing a lot of the information in this state. This alpha and beta could be any numbers normalized to 1. Okay, so it's actually, so we won't go through it in this lecture, but there's a known theoretical limits of how well you can uh, uh, measure or estimate what a state is, given that you don't know it, and uh, the best possible measurements to do it. So even with the fanciest possible measurements, so you've got some fancy, we've just only done very simple quantum mechanical measurements in this course, but you can do some more complex types of measurements. But it's known that there are fundamental limits on how well you can estimate an unknown state. So here's our unknown state psi. And if Alice has like n copies of the same state, then with more and more copies of the state, she can kind of narrow in on the actual state, right? So the more copies she's got, the better she can estimate the state. So n is the number of copies. So if she's got like a huge number of states, then this is like large number plus 1 divided by large number plus 2. So this number is always less than 1, but it gets closer and closer to 1, as in her estimate of the state gets closer and closer to 1 as n becomes large, right? So here she's got a whole bunch of copies of the state. They're all in the state psi. She's doing her fancy measurement, and after that whole process, she can work out that her state is most probably this psi estimate state. And from that, she could phone up Bob, and then Bob happily says, okay, let's go with that state that you just, estimated, and he'll go and prepare that state. Okay. So this is, again, it's still not teleportation. I'm basically, what I'm doing, why I'm telling you all this is to basically tell you that if you've got an unknown state, it's actually really hard to be able to know what it is and then just tell Bob what it is. So the thing that you take for granted classically cannot be done really very well quantum mechanically. And so for one qubit, using this one, putting in n equals 1 here, that's one and only one copy of your unknown state. The best fidelity you can do is 2/3, so 66%. So you can only basically estimate, an unknown quantum state on average to about 66%. So you're not going to do a very good job with this whole strategy of trying to work out what your state is, tell Bob what it is, and Bob goes and prepares it. Okay, so basically this strategy is not a very good kind of strategy. So what I want to show you now is finally the actual teleportation circuit. So this teleportation circuit allows you to actually transfer this unknown quantum state that Alice has and send it over to Bob with theoretically under ideal conditions, no noise or whatever, with 100% fidelity, 100% accuracy. You can transfer this state even though you don't know what it is, even though you never find out what it actually is. Alice never finds out what it is. Bob also never knows what it is, but they can actually transfer this state over from here to here. And in fact, you can in principle do this over kind of any distances as long as you can create the entanglement between. Okay, so I hope that this is sort of now set up why doing this is sort of a kind of a remarkable kind of process. Okay, so hopefully you can better appreciate what we're leading to here. Okay, so this is the quantum circuit that achieves the teleportation. So it kind of looks like this. So some Hadamard gates, these C0 gates. There's some measurements, and these red lines here are. This is like a classical communication step. So Alice still does need to tell Bob something, but it's actually not anything to do really with this quantum state. It's some other information that she needs to tell Bob, which I'll go through. And provided she can tell Bob that, Bob can perfectly get Alice's state. Okay, so we'll go through this sort of step by step. Okay. All right. So the way that this works is this circuit works. It can be broken into three main parts. Okay. So the first part is this blue section here. This part of the circuit, basically the purpose of that is to create an entangled state. So we've already met entangled states, I think, earlier in this course. So basically the part of this part of the circuit, the sole purpose of that is to create some entangled state. Okay. The second part of the circuit is actually a measurement in the so-called Bell basis. And what this is it's actually doing a measurement in an entangled state basis. So I'll explain what that is shortly. And thirdly, there's this stuff with the classical kind of transmission of information. So as I said, Alice needs to tell Bob some information, like phones up Bob. Hey Bob, I've got some information here. Based on that, Bob does some stuff, some operations. After these 3 steps, Bob will perfectly get the state that Alice had. Alice and Bob do not need to know what the state even is. Okay, all they need to do is follow this deterministic kind of sequence of gates. So they just do the same kind of gates with the same rules, and they will achieve this kind of teleportation. Okay, so let's go through each part. So firstly, let's look at this first part, which is the entanglement generation part. Okay, so we talked about the swap circuit in the previous lecture, and when we did that, what we did was to go through the circuit, draw kind of a time slice through the circuit. This is like your YouTube video, scroll bar, where you're going through in a time sequence. So basically, at each vertical line, each point in time, there is a particular quantum state. And so what we're just going to do is to work out what that quantum state is at each time. Okay, so here's our initial state. We've got some state psi. So these are all qubits, of course. So psi is in some unknown qubit state, and Allison, sorry, the other 2 qubits are initialized to the state 0. Okay, so that's our initial state. The first step is to apply a Hadamard gate on the second qubit here that is held by Alice. Okay, so what we do here to work out what the state here at T1 here is to apply a Hadamard gate on the state that we had on the previous slide, which was the initial state T0, and that will get us the state at T1. And Hadamard gate, just to remind you, is that unitary gate that is defined like this. And basically what this does is that if you apply the Hadamard gate to the state 0, it will make the state plus, as in plus is that state 0 plus 1. And Hadamard gate applied on 1 makes the state 0 minus 1, or the state minus. Okay, so when the Hadamard gate is applied on the state 0, it will make the state plus. So basically the second qubit here is this plus state. First qubit state is unchanged, it's still psi, and the third qubit is still on state 0. And if you like, we can expand this out. And so these 2 terms here will be 0, 0, and 1, 0. I've just combined, basically expanded this state out, and used the definition that the state 0, 0 is this state here, 0 times 0. Okay, so that's first step, simple enough. Okay, now let's go to step forward here, and what happens here is we apply a controlled NOT, and the control NOT has the control qubit on the second qubit, and the third qubit, which is held by Bob, is the target qubit here. Okay, so the state here at T2 is the state T1, whatever we got on the previous slide, multiplied by the control NOT. And let's just, this is what we got on the previous slide, and here's our gate here. Now we're just going to go and apply our gate here on the second and third qubits, that because we can see on the circuit that's the 2 qubits that this control NOT is applied on. And remember, the controlled NOT, what it does is that if the control qubit, which is this one, is in the state 0, then it does nothing to the second qubit, the target qubit. If the control qubit is 1, then it will flip the second qubit, or the target qubit. We can just look at these two states here and basically work out what the operation is. So first, the target qubit is the second qubit here. Remember, here's the first qubit, second qubit, third qubit. So the second qubit here is 0, so it does nothing to this state. Here, the second qubit is 1. That's the target qubit is 1, so it will flip this third qubit here. So it will turn 1, 0 into 1, 1. Okay, and the 0, 0 it leaves untouched. So the state at this point of the circuit is going to be psi. Here, nothing has happened to this psi yet, right? So it's just still psi. And then the second and the third qubits have become this state. It's an entangled state. So actually, really, all this, first part of the circuit does is, as I explained at the beginning, it just makes this entangled state. Actually, you can make a teleportation circuit really with any other type of entangled state. I think before we mentioned that there were 4 types of Bell states. You could actually equally use different Bell states and it would still basically work. You need to actually modify the last part of the circuit to make it work in the correct way. But this is as good as choice as any, basically. So in sort of the physical space, this is the situation that we have now. Alice is here. She's got her state that she wants to teleport. She's got her second qubit here. Now it's entangled with Bob's qubit. Now, this dotted line this is what I mean by kind of an entangled state. And these guys could be separated by a large distance. That part doesn't really matter. So we've got these 2 qubits, they're entangled, and first qubit, nothing has happened to it still. Okay, now let's move on to the second part of the circuit, which is this measurement in the Bell state, Bell basis, right? So actually, this is a perfect example of what I was talking about in lecture 14, where if you have some kind of unitary gate in front of some measurements, what this actually corresponds to is to change the basis of the measurements. So even though our measurements are all done just in the 0, 1 basis, we can actually make a more complicated, more general measurement just by putting some unitary gate in front of here, so just some gates in front of here, and that will actually make a much more general set of measurements. And it so happens that what this stuff here does is to make the measurements in this so-called Bell basis. So here are the 4 Bell states. There's 2 qubits, so there are 4 states in total, because 2 to the power of 2 is 4. And basically what this combination here does is to measure in the Bell basis. Okay. Now that's maybe a kind of a simple way to view this, but maybe a more straightforward way just to understand this circuit is to just grind through the circuit and just go through step by step in understanding the various steps. So actually, even though what I said in this slide is true, if doesn't really kind of appeal to your intuition, then we'll do it just the more sort of straightforward way, which is to just go step by step through the circuit. So let's just do that. Let's just now go through to sort of the third time slice here. So at this point, basically what we want to do is we want to apply this controlled NOT between the first qubit and the second qubit. Okay, so to get from T3 from T2, which was just before this C0 here, we want to apply this controlled not here, where the control qubit is on the first qubit, and the state that we had at the end of the entanglement generation part, as in just right here, was this one. So, so let's just basically work out what the action of this C0 is. And so what we do is, okay, let's say our state initially is this alpha beta state, okay, totally general state there. And let's just expand it out just so that we can easily work out what the action of the C0 here is. So just expand this whole stuff out. So 0 and 0, 0 gives 0, 0, 0. 0 and 1, 1 gives 0, 1, 1. 1 and 0, 0 gives 1, 0, 0. 1 and 1, 1 gives 1, 1, 1. Okay, and then the coefficients are alpha, alpha, beta, beta. Okay, we haven't applied the gate yet. That's still sitting out here. But now that we've written it in this form, it's easy to work out the action of it, because all we have to do is to apply our controlled not rule, which is to flip the second qubit dependent upon the state of the first qubit. Okay, so here we're going to be looking at these two qubits here, the 0, 0, those two. So because the first qubit is 0, we do nothing to the second one. Okay. Let's go to the second term. First qubit is 0. Again, we do nothing to this one. For this one, first qubit is 1, so we're going to flip the second qubit. So that's why this term is now turned into 1, 1, 0. These two, the earlier two terms, nothing happens to them. For the fourth term here, the first qubit is 1, so we flip the second qubit. That's why this becomes 1, 0, 1. Okay, so that's the new state after the C0, and that's perfectly fine as the state for there. But what we can just do is to do a little bit of factorization here by noticing that these two terms here, both of them start with 0, so we can just factor out that state there. They both have coefficients alpha, so we can equally write the first two terms like that, and the last two terms similarly. First qubit is 1, and they both have beta, so we can pull that out the front, and we have those two states factorized there. Okay, so that's state at T3. Okay, now let's apply this Hadamard, and the Hadamard is going to act on the first qubit, so that's why I've got a little 1 here, and that the state at T4 is going to be the Hadamard applied on the state T3. Okay, so as I said before, what the Hadamard does is turn 0 into plus state and then 1 into minus state. And this is acting on the first qubit. And so our Hadamard acting on, this is the expression that we got on the last slide. And so Hadamard acting on 0 becomes plus state. There we go. And Hadamard applied on the 1 state becomes minus state, 0 minus 1. Right. And that's, again, we can write it, that's perfectly fine as the answer, but let's just expand everything out and collect all the terms, well, or just write it out in this kind of 3-qubit form again, because this is going to make our life easier for the next step. Okay, so just expand everything out. 0, 0, 0 is that term. 0, 0, sorry, 0, 1, 1 is that term. 1, 0, 0 is that term. 1, 1, 1 is that term. 0, 1, 0 is that. 0, 0, 1 is that. 1, 1, 0 is that. 1, 0, 1 is that one. Okay. Okay, now here we're going to measure the first two qubits, and we're going to this measurement is always done in the 0, 1 basis. I think I mentioned that in the previous set of lectures. So now we measure the qubits in the 0, 1 basis, and actually what's just an easy way to do this kind of step here is to write the states already kind of collecting all the terms that you get with each measurement result. And so what I mean by that is, for example, So this is the state that we had here at this state just prior to the measurement. What we can do is just collect all the terms with the 0, 0. So, for example, this term here has 0, 0 as the first 2 qubits, right? There's actually another term over here which also has 0, 0 as the first 2 qubits. Now, because the measurement on the first 2 qubits will collapse the state to one of the 4 cases of 0, 0, 0, 1, 1, 0, 1, 1. It's actually kind of simple, easy way to work out the effect of the measurement by already kind of factorizing these first 2 qubits, so that in the case that you measure to 0, 0, then this is the state that you're going to get on the third qubit. For this term here, I've collected all the terms that have 0, 1 for the first 2 qubits, so that would be that term and that term here. So these 2 terms here have 0, 1 as the first 2 qubits, and so this the thing that you're going to have on the third qubit is this alpha over 2, 1, and 0 state, and beta over 2. Okay, 1, 0 for the first 2 qubits. We got this one and this term here, and if we collect these two terms together, then we'll get this state here, and the last one is 1, 1, that term, and so we'll have this state here on the third qubit. Okay, writing it like that kind of makes our job of figuring out what the state is after the measurement a little bit easier. Okay, so now let's go and actually do that measurement. So I just copied that equation on the last slide there, just over here. This is the same state. And doing that measurement will randomly collapse the state to one of these 4 terms here. So either this one, this one, this one, or this one. Okay, and you can work that out using your measurement operator method, or maybe you can just read it off here. But basically, because we've collected all the terms together for each of the different outcomes, then we will get one of these 4 measurements when we do this measurement step here. Okay, doesn't matter actually whether you do the measurements simultaneously or slightly, one slightly before the other. It doesn't really matter. You will get basically these 4 outcomes either way. In terms of the probabilities, you can again use your measurement operator method to work out that the probabilities are a quarter for each outcome. And basically the reason why is because apart from this a half coefficient here, this state here, like here, is actually like a normalized state, because this is alpha, beta, that's normalized. 0, 0 is normalized, so it's all normalized. Likewise, this is another normalized state. 0, 1 is normalized. This is normalized, and so is this. So the only thing that you need to really worry about in terms of the probabilities is actually just this factor here, and the square of a half is a quarter, and so that's why you have a quarter for the probabilities of each of these different outcomes. Okay, so fine, that's the end of the second part of the circuit, and so we basically randomly have these 4 different outcomes. Okay, so that's basically what happens at that point. So what we actually notice already is that it actually looks nearly like we are there already with the teleportation, but just not quite. So for example, let's look at this first outcome here. So in the case that Alice gets 0, 0, then Bob actually has the state alpha 0 plus beta 1. That's exactly the state that Alice started off with. So at least for this case, Bob, job done. Teleportation has been completed. The only problem here is that that doesn't always happen. 3/4 of the time, Bob actually ends up with a different state. But actually, even those three other cases are like pretty close to what it's supposed to be. For example, in the case that Alice gets 0, 1, Bob actually has this state alpha 1 plus beta 0. Now that looks a lot like the state that Alice started with, which was actually alpha 0, beta 1. It's just that like these are like the wrong way around, right? So the 1 was supposed to be 0 and the 0 is supposed to be a 1. So these are kind of flipped around. Okay, so apart from that it's just got a bit distorted in the process, but it's kind of very similar, right? Similarly with the state 1, 0, the only problem here is that instead of alpha 0, beta 1, we've got some minus sign here that's got in the way. If this minus sign wasn't here, if this was a plus sign, everything would be fine. The teleportation would be done. And likewise here, if Alice gets 1, 1, then the state that Bob gets is alpha 1, beta 0. Actually, this is kind of got both of the problems. If this sign wasn't here and also these two were flipped, then it would be all good, right? So so basically, the at the end of this this point in the circuit, the teleportation is kind of there, but it's just that 3/4 of the time Bob's state is a bit mucked up. So all we need to do actually is to fix up these three cases that Bob is getting these weird flips, phase flips and bit flips and things like that. And then the teleportation would actually work perfectly, right? So just to give you an example of that, so let's consider the case where Alice and Bob, they follow this procedure, and then on this particular run, Alice gets the result 1, 0. Okay, so this is a case where we know that Bob will actually get the state alpha 0 minus beta 1. So basically this state is fine up to the fact that this has the wrong sign here. Okay, so everything looks good except for the fact that this beta has actually got the wrong sign in front of it. So this is basically what they can do to fix up the actual state that Bob has. So because Alice actually knows what she gets, she's done a measurement, right? If you've done a measurement, you know what that outcome is because you've just done the measurement and it's random, but you know for that case that you've got, say, 1, 0. Yeah, so Alice has done her measurement and she gets 1, 0. So this is what she does. So she says, she calls up Bob just on her phone and she says, "Hi Bob, I've just measured my qubits and I've got the case 1, 0. Now because they've already worked out what this circuit is actually going to do, then Bob, because he knows that if Alice is going to get 1, 0, then the state that he'll have should be the state, but just with an extra minus sign. Now he can get rid of that minus sign by applying a Z gate, because remember, a Z gate, what it does is if you've got a state like, sorry, here we go, you got Z, then what this does for state 0, it just doesn't change 0, and Z applied to 1 will add a minus 1 to it. So that means if you add a Z to this, then just on the 1, it will make an extra minus sign and get rid of that minus sign. So that's all Bob needs to do, and the Z gate is a unitary gate, so he can totally do that. Yeah. So by doing this, and there's some similar things that you could do for all other cases. So for the first case, Bob doesn't have to do anything. So Alice just calls up Bob and says, I got 0, 0, and Bob goes, oh good, I don't need to do anything. And if she gets 0, 1, then Bob does some other operation, and all the 4 cases Bob can do it. Bob can adjust his state so that it's the right state. So here's basically all the 4 cases, just in a neat table. So here's the 0, 0 case. This is the case where Bob doesn't have to do anything. So Bob's state is already alpha 0, beta 1. So after doing nothing, it's still that state, of course. For the outcome 0, 1, we know that the state is this state with where the 0 and 1 needs to be flipped. So Bob needs to do an X gate. An X gate is the thing that will flip the 0 and 1. So after that, he'll get the proper state. We already talked about this one. That was a case in the last slide where we get rid of this minus sign on the 1. And this case here where it's like alpha 1, beta 0, this is like both of these 2 cases combined. So in this case, what we need to do is we need to flip the bit so that when you flip the bit, that will turn into that. And then you need to add a Z gate to get rid of the minus sign. And then after you do that, you will get the proper state. So basically, for each of the cases, Bob will get the correct state so long that he does this correction. And the reason why this circuit looks like this is because, if you notice, the cases we need to apply an X are also the cases where Alice's second qubit is 1. So basically, if Alice's second qubit is 1, then Bob will need to do an X. So Alice's second qubit is this one. If it's 1, Bob does an X. If it's 0, then he doesn't do an X. Okay. Now the cases where Bob needs to do a Z, also the cases when Alice's qubit are both 1. So again, when Alice's first qubit is 1, then Bob needs to do the Z gate. If Alice's first qubit is 0, then Bob doesn't need to do any of those. Right. Okay. So that's basically the last step, the classical correction, and this basically completes the teleportation protocol. So just to recap, so what has this done? So Bob has basically received Alice's state, and if you go through this circuit here, Alice and Bob, they both, they didn't need to know what this state is at any point in time. All they need to do is apply this sequence of gates. Even in the measurement step, Alice just gets these 4 cases with probability 1/4 each one. That doesn't actually tell you anything about the state. It's just some random, like throwing a dice. And all she needs to do is tell Bob what that is, and then Bob can apply some gates. Bob also doesn't know what this state is, but he can be sure that it is the state that Alice originally had. So neither of them know what the state is. So I just, of course, make the point that it's also fine that they do know what the state is. I mean, in fact, if you are, an experimentalist working in the lab, it's probably better that you know what the state is that you're actually transferring, but it's kind of the principle that counts, that you don't need to know what the state is. And the main things that you actually need to do this teleportation are just these entangled qubits between Alice and Bob, and also Alice also needs to tell Bob her measurement outcomes that she actually got. Right? And as I was explaining in the earlier part, so the one of the important aspects of this is that actually the fidelity, as in the how well you can transmit this, is actually perfect. So even though they don't ever know what the state is, they can actually do a perfect transmission of this state. And so this is actually better than any state estimation method, as in, better than any method where you try and measure the state and then just tell Bob what it is. This is actually superior to any method like that. So you might be, wondering that if you can sort of do this kind of thing, then it almost looks like because this you don't really tell any information about the state. So unlike the first methods where you ring up Bob and then you tell Bob, hey, I've got this particular state. All you do is you just send a couple of bits of information. Um, you know, it almost looks like there's no limits to how far that you can perform this teleportation. And actually, so in a way, this is true. So you could, in principle, actually do this teleportation over arbitrary distances. So if you were able to set up entanglement between, say, different galaxies, different ends of the universe, there's actually no real limit uh, to the distance that you can perform your teleportation. Right? But the only catch is that in order to complete your teleportation protocol, you need to actually do that classical correction step. So unless you you phone up Bob and then you tell Bob, which measurement outcome you got, you can't really complete the actual protocol, and because that classical step um, can only go at the fastest speed that can go is at the speed of light. You basically can't complete the protocol until you get that classical message, and so that's why you can't really do the full teleportation. But it almost looks like it comes extremely close to be able to do this, and so it's kind of a fascinating sort of exercise in how quantum mechanics kind of works over large distances. And there's been a lot of research done in this kind of aspect, and some people are even saying that maybe entanglement can be viewed as something like a wormhole in space, and I'm not really sure if that's something which is going to be true or not, but there's still a lot of exciting research that's being done right now. Okay, so that caps off this lecture and this course. So I hope that you learnt something from all these lectures. If you are interested in any of the materials that we talked about here, then I encourage you to continue looking up stuff on quantum information. It's really just scratches the surface. And if you have any questions, then let me know. And yeah, and thanks for your attention. So see you later.